Electrochemical cells. This is a diagram of what's called a voltaic cell, something we'll be looking at in a lot more detail in just a few minutes. Electrochemistry, the study of the interchange of chemical and electrical energy during a redox reaction. Going from chemical energy to electrical energy, we can again look at a voltaic cell. This is a spontaneous reaction. Electrons come from the zinc, which is being oxidized, to the ions in solution down here, which are being reduced. Now that is spontaneous. Chemical energy to electrical energy is spontaneous. This is like a simple battery. Now, to cause the electrons to go in the opposite direction, we need to supply some sort of power source, cause the electrons to go in the opposite direction. Now that's non-spontaneous. So you can think of this as a simple battery, and you can think of this as a battery charger. The battery discharges while the reaction is taking place. So it's like the battery running down, and going in the opposite direction, we charge the battery. So going from chemical energy to electrical energy is often referred to as the reaction discharging, and going from electrical energy to chemical energy, the reaction is being charged. What is electricity? Electricity is the flow of electrons from one point to another. Some examples of the transfer of electricity, of electrons from one point to another. When you shock somebody, electrical transformers, lightning, an electrical circuit. Okay, now speaking of electrical circuits must be closed in order to conduct electricity. This is what happens when you turn on a light switch. Now this is called an open circuit. The battery, the wires that are connecting the battery to the light bulb are broken. So it's an open circuit. In order for electrons to flow through this circuit, I need to close the circuit, and then electrons can travel through. So this is when you turn on a light, and when you break the circuit, that is turning off the light. We'll refer back to, I'll refer you back to this in a few minutes. A closed circuit. Voltage, the measurement of electrical pressure or potential between two oppositely charged points. So if you had a negative plate and a positive plate, and you put an electron between them, well, that electron is going to be attracted to the positive plate. The kind of the force of that attraction, or the pressure of that attraction, is measured in units called volts. So when you look at a battery and it has a positive and a negative post, whatever the voltage is of that battery is a measure of that attraction that the electrons would have going from one point to another point. As we'll see, the negative post is a site of oxidation. So you have oxidation taking place here. You have reduction taking place here. Voltage is analogous to the pressure of water passing through a hose. So if you were to turn the faucet on higher, the water pressure would increase. If you turned it down, the pressure would decrease. Voltaic cell, an electrochemical cell that generates electrical energy from a spontaneous redox reaction. And it's named after Alessandro Volta, an Italian physicist who invented the first battery in 1800. He didn't invent electricity, he just harnessed it. This is a very simple representation of what he did. It's called a voltaic cell. A more complex and useful product was called a voltaic pile, and this was the first battery. Okay, I'm going to show you a short video to introduce electrochemical cells.
If we place two different metals in salt solution and connect them, an electric current flows. This is the basis of the batteries that power everything, from mobile phones to milk floats. But how does it work? To understand this, we need to describe how electricity is produced by electrochemical cells. Explain the movement of electrons when two half cells are connected. A simple electrode, or half cell, can be set up by placing a metal rod into a solution of its own ions. To set up a zinc half cell, a zinc rod is placed into a solution of zinc sulfate. Once in the solution, some of the atoms in the rod release electrons and form ions, which dissolve. The rod is now negatively charged relative to the solution, giving it a negative electrical potential. This causes zinc ions in the solution to accept electrons and form zinc atoms. An equilibrium will be established. If the electrical potential could be measured, it would tell us how easily electrons are released by the metal. That is, how good a reducing agent it is. However, electrical potential cannot be measured directly. If we connect two electrodes, we can measure the potential difference between them using a voltmeter. Here is a copper electrode. It is made in the same way as the zinc electrode. The electrodes are connected by a salt bridge. This is usually a piece of filter paper soaked in saturated potassium nitrate solution. The voltmeter is measuring the potential difference. The potential difference of this cell under standard conditions is 1.1 volts. The zinc electrode is more negative than the copper electrode, so zinc is a better reducing agent. If the voltmeter were removed, electrons would flow from the zinc electrode to the copper electrode. Different cells have different potential differences. If the copper electrode is changed to a silver electrode, the potential difference is 1.56 volts.
Okay, we're going to diagram all the parts of a voltaic cell. Now this is going to take a lot of discussion, so please make the drawing that you have in your notebook large, maybe an entire page for this. Okay, this is a piece of metal that's immersed in a solution that contains ions. So like if this was zinc, this solution would be zinc chloride, say. If this was copper, then this would be copper chloride or copper sulfate or something like that. This is called a salt bridge. It contains sodium chloride or any other ionic compound. We'll talk about that in a minute. And a voltmeter that we can use to read the voltage of our cell. Okay, so each one of these, and we can think of these as beakers. At school, we build these very simply. I'll probably show you one as a demo. This is a beaker. Each beaker is referred to as a half cell. Together, we have our voltaic cell. The more active metal is called the anode, and it's the negative post. So on a battery, when you see a negative post, that's the anode, more active metal. Atoms are oxidized by the more active metal. Ions go into solution. The anode loses mass. And so as this reaction proceeds, the atoms that make up the more active metal turn into ions, go into solution. So slowly the anode corrodes away. The reaction that takes place is oxidation. So oxidation is taking place in the half cell of the anode. Now the anode loses electrons. Oxidation is the loss of electrons. And so electrons go over to the other half cell. Now the electrons don't react with the metal there. It reacts with the ions in the solution, ions of that metal. Okay, so this is the less active metal. This is called the cathode. This is the positive post of a battery. Ions are reduced. The cathode gains mass. And so as electrons come in, the ions in solution are reduced, becoming atoms, and they adhere to the metal electrode. So this is reduction. Now remember, talked about in order for electricity to flow, we have to have a closed circuit. So when we have electrons going from the half cell here over to the half cell here, unless there's some way to complete that circuit, it won't run. So that's what the salt bridge does. The salt bridge completes the circuit. The negative ions in the salt bridge go in the same direction as the electrons. And so in this example, the electrons are going clockwise. So as the electrons enter here, the anions in the salt bridge are going clockwise. The cations are going in the opposite direction. So the anions go to the anode, the cations go to the cathode. Cell notation. This is a way that we can easily represent a voltaic cell. And the way that this works is that we first write the metal, and it's with its phase, it's solid, and then a straight line to separate it from the ion that it becomes. And when it becomes an ion, it'll be aqueous. Then we use a double line here to separate the two half cells. You can think of it as the salt bridge. So the two double lines here, the salt bridge. On the right side, we have the half cell where reduction is taking place. And so we have an aqueous ion being reduced to its elemental state. It's important that you do it exactly in this order. So it's the metal, and then the metal's ion, double lines, the ion, single line, metal. All the ions are aqueous, all the metals are solid. So the oxidation half on the left, the reduction half on the right. Now in your homework, this is what I'll give you, is a chemical cell, or the cell notation, and ask you to diagram a voltaic cell based upon that. I'm going to show you a little animation that gives you a better sense of the flow of electrons and ions.
In a voltaic electrochemical cell, an oxidation occurs at an electrode called the anode. The electrons released at the anode travel through a wire to another electrode called the cathode, where the electrons are consumed in a reduction reaction. Anions are then shuttled through a salt bridge from the cathode compartment to the anode compartment. Otherwise, a net negative charge would build up in the cathode compartment. The negative charges move in a circuit through the cell.
Okay, so you can see over on the left here, the anode, when it's being when oxidation takes place, you can see that electrons, there are little red dots here coming off in a second there. So electrons are traveling over here, and they go through and then react with the cations in solution. The anions that are in the salt that are in solution travel through the salt bridge to complete the circuit. So you can see as time goes by, the anode is losing mass and the cathode is gaining mass. In IBChem 2, you actually measure or calculate the mass lost over a certain amount of time and the mass gained. Okay, in the lab, we use a voltmeter to measure the voltage for the particular voltaic cell, which would vary depending upon the metals that are being used. We're going to be using an online voltmeter, and you'll need to be able to do this for your homework. So in this particular voltaic cell, I have zinc in a solution containing the zinc ion and copper in a solution containing the copper ion. So here's a link for it. Okay, now the way this works, you see these are our two half cells here. I will pick the zinc as my electrode, and it's in a solution, and it doesn't matter what the ion or the solution is, it just needs to have the zinc ion. So zinc nitrate, it could be zinc chloride or sulfate, it doesn't matter. It just needs to be a solution containing that electrode. So zinc. And then copper here in a solution of copper, copper to nitrate. Now to measure it, all you need to do is click on Measure Cell Voltage, and you get 1.100 volts or voltage. Let's do practice. On the diagram below, label the direction of the electron flow. Use the activity series to determine the more active metal. So using this as our activity series, we can see that zinc is more active than iron. So zinc is going to undergo oxidation. It will lose electrons. And so that is the anode, negatively charged, and the cathode is positive charged. The cathode is the electrode that is less active. Now for the flow of electrons, just remember, or for the signs, just remember that electrons are negatively charged, so they're going to be attracted to the positive cathode and repelled by the negative anode. Okay, the direction of the ion flow in the salt bridge, so remember that the electrons flow, in this case, are flowing counterclockwise. So the ions in the salt bridge, or the anion in the salt bridge, needs to go in that same counterclockwise direction. So the chloride is going counterclockwise along with the electrons. The cell voltage, use the online voltmeter. Okay, so I have iron and zinc. So iron on the left, zinc on the right. So iron, zinc, iron 3 nitrate, zinc, and zinc 3 nitrate. Or zinc nitrate. There's no zinc 3, zinc nitrate. Okay, now when I measure this, if I was to measure it as it's set up, I'm going to get a negative voltage. Negative. Now that's because on the left side here, this is the anode, on the right side is the cathode. But don't worry about that. Just put in the metal and the ion and the solution for that metal, and for on both sides. And if you get a negative reading, just make it a positive value. So if I went to the trouble of switching the electrodes, I would end up getting a positive 3.22. But I'm not going to worry about that, nor should you. So the voltage is 0.322. Write the associated redox equations for this voltaic cell, including phases. So the oxidation half is the zinc undergoing oxidation. The reduction half is the iron 3 ions undergoing reduction. Now the overall balanced equation would be the sum of those two half reactions. But remember, we need to have the same number of electrons. So I need to multiply the oxidation half by 3 and the reduction half by 2. When I do that, the electrons will cancel out, and I'll have the overall balanced ionic equation. 3 zincs plus 2 iron 3 ions give us 3 zinc ions and 2 irons. The cell notation, oxidation, reduction. Okay, and this is just FYI, just in case you should see this at some point in time. Rather than a salt bridge, a porous disk can be used that allows the anions already in solution to complete the circuit. So rather than a salt bridge, you can have this semi-permeable porous disk, and the anions in the solution, in this case would be sulfate, can transfer through to complete the circuit. Just another way. It's the same concept, just a different way of closing the circuit. All right, now this was all voltaic cells. There's another type of electrochemical cell that we need to talk about, and that's called electrolytic cells. Electrolytic cell, a chemical cell that uses a power source to reverse a spontaneous redox reaction, a process called electrolysis. Electrolysis, the use of electrical energy to bring about a chemical change. Here's an example.
The decomposition of water is thermodynamically disfavored, but can be made to occur by electrolysis, the application of an external electric current. Here, platinum electrodes transfer electrons between two cell compartments to separate the decomposition products. Gaseous oxygen rises from the anode at the left, hydrogen from the cathode at the right.
And here are the two half reactions. You don't need to know these, but thought you might want to see them. Now, one thing I should point out here is electricity does not flow through water without there being some sort of electrolyte dissolved in the water. And so we have something in here, I don't know what they used, but something to allow electricity to be conducted through it and for the electrolysis of water to take place. Okay, let's look at the electrolysis of sodium chloride. This is the one that IB earmarks, the electrolysis of sodium chloride. Okay, now this is our electrolytic cell. Now notice we don't have two half cells. It's all contained in one container. We have molten ionic compound, which is an electrolyte. Now, sodium chloride has a very high melting point, 801 degrees Celsius. So at that temperature, solid sodium chloride, regular table salt, will melt. And that's what we have here. I know it kind of looks like water, but it's not. It's very important that you understand it's not aqueous, it's liquid, liquid electrolyte. The electrodes that are immersed in the electrolyte are either platinum or carbon electrodes. These are inert. They don't take part in the chemical reaction. For the carbon, just think of like a large pencil lead, which is what we use in the lab. This is our power source. This is a battery, and this is the symbol that we use for a power source. The longer line is the positive post of the battery, and the shorter line is the negative. Now, the power source, you kind of think of it like an electron pump. Electrons are going to be drawn to the positive, repelled by the negative. And so you need to look at the electrolyte to say, okay, what can lose electrons? Well, the ions will move towards the electrolyte, or ions move through the electrolyte to oppositely charged electrodes. So we have chloride ions and we have sodium ions. Which of the two will be attracted to the positive electrode? Well, of course, it would be the chloride ion. The chloride ion's negatively charged. So electrons will be leaving the chloride ion. Now, this is the anode. It's positive because it relates to the positive post of the battery. So positive, positive. Now, what specifically is the chloride ion going to undergo? Well, it's going to undergo oxidation. The chloride ion, when oxidized, becomes elemental chlorine and releases 2 electrons. Now, let me point out here that the anode for an electrolytic cell is positively charged, whereas the anode for a voltaic cell is negatively charged. We'll review this at the end. Okay, now the electrons, of course, are flowing through a circuit. So they're coming in to the electrolyte. Which of the ions in the electrolyte need electrons? Well, it would be the sodium ion. So the sodium ions will take in the electrons to be reduced. This is the cathode. The cathode for an electrolytic cell has a negative sign. And the cathode is the site of reduction. So sodium is undergoing reduction. Now, remember that it's a molten ionic compound, really, really hot. So when we talk about phases of the products, well, we really can't do that. It depends upon what the particular element is. Sodium, we would want to say solid, but at these temperatures, sodium would be a liquid. So don't worry about phases. At high temperatures, or the high temperatures make phases of the products uncertain. So you're not going to be responsible to know what the phases are for the oxidation and reduction half reactions. You should know that the ions are liquid, though, not aqueous. Okay, let's do some practice. We have aluminum bromide, molten aluminum bromide liquid. So it will always be molten. So our electrolyte here is filled with aluminum ions and bromide ions. On the diagram below, label the following: the direction of the electron flow. Well, for electrolytic cells, that's really easy. All you need to do is look at the battery. The electrons are going to be attracted to the positive post of the battery and repelled by the negative. So in this particular diagram, the electrons are traveling in a counterclockwise direction. The anode and the cathode, including their signs, will remember that the positive post of an electrolytic cell is the anode, and the negative is the cathode. The ions attracted to each electrode. Well, what is the source of the electrons in our electrolyte would be the bromide ions. So the bromide ions are going to be attracted to the positive post, they're negatively charged, and the aluminum ions, positively charged, will be attracted to the negative post. So here you're going to have oxidation taking place, and over here you're going to have reduction taking place. Write the redox equations for this electrolytic cell. So bromide is undergoing oxidation, losing electrons, forming elemental bromine diatomic, and the aluminum is being reduced to elemental aluminum. Again, we're leaving phases off. The overall balanced equation, well, we have 2 electrons here, 3 electrons here, so we need to multiply the oxidation half by 3, the reduction half by 2, and this would be our overall balanced ionic equation. Electrolysis can be used to obtain the purity, it can be used to obtain and purify reactive metals from common ores. Example is bauxite. Bauxite is the main source of aluminum, which consists mostly of the mineral gibbsite, which is aluminum hydroxide, which is chemically processed to produce aluminum oxide before electrolysis begins. So if you take this mineral, various chemical processes to reduce it to, well, using the term reduce figuratively, to aluminum oxide, and then have it undergo electrolysis to produce aluminum. Challenge question. What is the biggest expense in the purification of metals such as aluminum? So if we were to take this and remove the aluminum from it through the process of electrolysis, what do you think costs the most money to do that? And the answer is electricity. Their electric bill through the roof. Okay, let's compare anode versus cathode for the voltaic and electrolytic cells. Now, first off, the anode, whether it be voltaic or electrolytic cell, is always the site of oxidation. Likewise, cathode is always the site of reduction. What's different between them is the sign of the electrode. The anode is the negative electrode, because remember, for a voltaic cell, that's the site of oxidation. An atom loses electrons. Electrons are negatively charged. But for the electrolytic cell, that's the positive electrode, because remember, it's hooked up to a battery. Things are going in the opposite direction. The negative ion that is in the electrolyte is attracted to the positive post of the battery. So that is the site of oxidation. For the cathode, it's the positive electrode for a voltaic cell, and the electrons are being attracted to the positive ions in solution. For the electrolytic cell, it's the negative electrode where the positive electrolyte is attracted to the negative post of the battery. Now, all you really need to remember is that the anode is always the site of oxidation. The cathode is always the site of reduction. Remember, and then simply remember voltaic cell, the anode is negative, the cathode is positive. Then for the electrolytic cell, just remember that the signs are opposite. The positive electrode is the anode, the negative electrode is the cathode. Now, to remember what occurs at the anode, that it's always oxidation and the cathode's always reduction, there's a couple of mnemonic devices that might help. Oxidation always occurs at the anode, so O and A are both vowels. And reduction always occurs at the cathode. R and C are both consonants. Or you might use this. Anode oxidation, un-ox, and reduction cathode, red cat. So, like most mnemonic devices, the sillier it is, the easier it is to remember. So take it or leave it. Okay, boys and girls, and all in between. That is it. End of notes.